Okay, here is where we stopped, and from the last video. And in this case, we have to add the rich links. So you come to tables and say add rich links. So this is for station 10. This will be the difference between some point of interest to the station 10, where the river reaches, the river cross section starts. So we can assume certain distance for this rather than considering this large value. Like let's consider like 50 meters, for example, 50 meters from a point of consideration. So we have to copy this, and this also beats a bit. This will also look like a bit of an error, because the distance should at least counteract each other, and maybe you would like to edit these 2 pointers. So let this be like 15. If this 15, this will be larger as well. Okay, whatever, let's take as it is, and it doesn't matter. So copy this one and go to your table, and then Ctrl+V, say OK, and here is your reaches. So you have your reaches, and you can now you can edit any pointers that you have in here. So in order to if you see here, if the color is deep green, it implies the georeferenced user entered cross section, and this one is georeferenced interpolated cross section, non-georeferenced user entered cross section. So we are going to GIS tool and sketch line, accept the display locations as georeferenced. So for all of the nodes, and then say OK. So it is being converted to green, which is correct value. So now we have input the rich values, and we have to enter the Manning's coefficient here again. Manning's coefficient at the left bank, in the middle, and the right bank. So at the banks, the coefficient will be higher, and at the center it will be lower. If you consider like 0.5 at banks, and 0.3 at the center, and 0.5 at the other bank again. Sorry. 0.05, 0.03, 0.05. So you can have 10 of this. So 1, 2, 3, 4, 5, 6, 7, 9, 10. So for each station we have to input a different values if it is a reality, but in this case this will do it. So copy this and add it to your n values, so, and say OK. Now the second step is or the next step is to fix the left banks and the right bank extents. So if you look at the cross section, now from the input data you have the left bank and the right bank distances for the first one, for station 10, and this is the Manning's value, and we have to select the left bank and the right bank station now. So for that we can use this one. So if you see these red dot pointers, it will show you where you like to select the bank. So this is the left bank. If we can move it toward this, and let's consider this point as a left bank is, and let's consider this one as the right bank. So you have to push a bit to this point, and then you have to change, and then let's consider this point to be the left bank and this point to be the right bank. And then for 8, let's let this be the left bank, and let this be the right bank, and for 7 let this be your bank, and for right bank this might be your bank, and for 6 consider this point to be your left bank, and this one to be right bank, and for 5 let's consider again this is to be the left bank and this be the right bank, and in this case let this be the left bank and this be the right bank, and let's consider let's consider this be the right bank, this be the left bank, and same thing here. Let's consider this to be the left bank and this point itself to be the right bank, and let this be your left bank, and let's leave this one as it is. So we have edited this one, and then you can leave. So you can see the dotted pointers, they will show the cross sections, and now I can save the geometry data. Okay, so we have inputted any geometrical data required, and we have tabbed them, and we have to go to the additional parameters we might need, and basically other than geometric data, the required data is steady flow data. So once we have saved and we finish this with this one, we can close it, and in this case this is for the steady flow data. Okay, and you can see the rich boundary condition. So we don't have any data about the flow condition in the river. So in most of the time the good way is to provide rating curves, and that is very interesting way of doing the analysis, but we can input the normal depths of 0.3 meter, for example. Okay, this for all stations. Let's consider this one, and now here we need to create the different return periods floods. So in the normal ways, what you have to do is you have to do the distribution types. There are different distribution types depending on frequency analysis. You have several distribution types like the Gimbel's meter, the Weibull the meters, and the Wakebi meters, and so you can choose one of them depending on how close they are. So once you have the flow data, for example, so you have to find the moment ratio diagram, or we have to draw the moment ratio diagram. So this is a moment ratio diagram, the coefficient of kurtosis on the y-axis and the coefficient of skewness on the x-axis, and then this curves represents a 3-parameter distribution type, and this dot point represents the dot points for this one represents 2-parameter distribution types. So if you what you have to do is you have to plot the kurtosis and the skewness of your station over these distribution types. Then the point to which your site or your river kurtosis skewness plot gets closer will be the distribution type for that particular watershed. So for example, these are the datas. Okay, these are the datas. If you see the dot green datas, they are closer to the green line, which means they follow the Wakebi lower bound distribution type. And if you see, for example, this one, this blue one, so it is closer to blue, so the blue distribution types will be the generalized, the general extreme value approach. So Based on that, once you find these ones, you have to estimate your parameters by using one of the approach like the maximum likelihood, the conventional moment approach, or the probability weighted moment approach. So from that you can fix your flood with several return pairs. So you can enter those values here, and for different return pairs, let's consider, for example, let's assume we don't have any data for this, and let's assume a t return period in years, 5 year, 10 year, 15, 25, 50, 100, and 200, and 1000 return period floods. So 1, 2, 3, 4, 5, 6, 7, and 8. So we have to create eight boxes here. So 8. Okay, and then say apply data. So we have eight pointers, and we have to assume certain queues discharges for these return pairs. Let's consider this to be 0.5, 1.2, 2.0, for example, and 5 meter cube per second, 400, maybe 10, for 200, maybe 20, for 1000, maybe 50 meter cubes. So you have to copy this data, the flow data, and for different return pairs, you have to remember the order of the return pairs, and then you can paste them here. So these are different floods. You can see these ones. You can edit them if you want. So with this, you can save your flow data into the same folder. You can save flow data, full flow data. So if you say OK, and you exit this one, so you have now your flow data, you have your everything you need, and you can run your model for steady states. So this is where we run the model for steady states, and so let's consider for subcritical flow, and say compute. So it has been run successfully. So now you can view the results, and if you want to see the 3D flow, the 3D water flows, so this is for you can see this to be for PF1, which means for 5 year return periods, and you can view for different year return period. You can view the data. Actually, you can do this. This is for PF1, and this is for PF2, for PF3, PF4, PF5, PF6, and PF7, PF8, which means this is for a 1000 year return period flow, and at the same time you can also view the water surface profile. This is a general profile of the water in the channel, and also you can see the profile of water in this way: the energy grade line, the water surface profile, and the critical surface profile. And you can come here in this, and you can see your cross sections with water. This is how cross section 1 responds to condition 8, which means for 1000 return period flood. And you can see this for 2, for 10, for 9, for 8, for 3, 7, 6. You can see for every conditions. So you can change this data. You can view it for different condition. Okay, and yeah, view, you can say, you can see the water surface profile the same way for different conditions. Okay, this is for PF8. For PF1 it looks like this one, for PF2 to this one, PF3, PF4, PF5, which means for different return period flows. So PF1, PF2 means it is this one. This is PF1. Okay, this is PF2, and to PF8. So these are those data, and yeah, you can see the different conditions you might be able to see under different circumstances. Okay, so this is flow in every cross sections for different return period. This is for a 5 year, and for different return period you can see how the level increases. So you can and then the other important data is you can go to view and see the so this one, profile summary table. So this will indicate the flow with this return period. Okay, this is the PF8. So for PF8, for this much at every reach, and this much minimum channel elevation, this much water surface, this is the critical water surfaces, energy gray lines, the energy gray line slope, the velocity in the channel, and the flow area, the top bodies of your river, and the Froude number. And you can see every Froude number is less than 1, and you can tell that is a critical flow. So this is how for if you want for different condition, you can just run for you can just see it, you can see the data for under different circumstances. Okay. Okay, you can so this is how HECRAS model can be run by using surveying data.